Welcome to a lesson with Dr. Powell. Let's take a look at an example of solving a system of equations. We'll do this in two parts. The first part we'll cover in the first video of this example, and the second part in the second video. The first part involves finding reduced row echelon form, and the second part involves doing some column operations. First, we're going to find just one solution to this system. And then in part two, we will expand that one solution to all solutions of the system. Okay, so how do we begin? Well, it's how we see and look at this system of equations. We can think of this as being simply a linear combination, where we have x times a column right here, y times a column, z times a column. So these are different vectors, and x, y, and z are scalars. And so we have a linear combination of column vectors. And we'd like this right here to represent the outcome of this linear combination. So we've chosen scalars such that this is the outcome. Another way of looking at this is thinking of x, y, z as being input into a function like this, a matrix function with a column interpretation, and the result is simply this linear combination. And if we'd like the result to be equal to this, then what we're looking for is the fiber over this codomain element, meaning what are all the vectors that map to this point. Okay, so now how are we going to do this? Well, in part one, we're just going to find one example of x, y, and z that works. So to help us do that better, we'd like to look at the situation in a simpler setting, meaning we're going to plug in this linear combination, which is equal to this. So plug in everything right here into a linear transformation. That's going to simplify things. The linear transformation that we're going to plug everything into is a row operation. Now, linear transformations preserve linear combinations. And this linear transformation that we're going to do is reversible as well. So what does that mean? That means that we have a reversible linear transformation that which preserves linear combinations. So if we were to take the image of this vector in the transformation and this one and multiply them by these scalars, it would be the same as first performing this computation with these scalars and then finding the image of the result, namely this. So this equation should hold even when we do the same linear transformation to this, and this. We'll have the exact same situation holding. Now, if we can find scalars x, y, and z that work in a simpler setting, because the transformation is reversible, we can go backwards and realize that this equation right here with the x, y, z that we choose actually works in the original setting as well. So we're going to apply a linear transformation. Now, the linear transformation that we apply, like I said, is a row operation. Well, we can do a row operation right here just between these guys, like what's happening right here, but we do the same thing to this and this and this. We do it all simultaneously. Okay, so we proceed by simply writing out all of these columns together, including this one, because we're going to form linear transformation, which is a row operation, to all of them at the same time. -4, 4, 1, -15, 14, 4, 26, -24, -7. And we just want to go just as far as we need to in order to see an easy example of what the scalars x, y, and z could be. Okay, so basically we're going to be using row operations as much as we can to get this towards Smith normal form. We won't be able to get there all the way, perhaps, but we go as far as we can, which means we get as many pivots as we can for the reduced row echelon form. So when we get a 1, if there is any spot to the left of it, we want those to be zeros. And up and down, we would like there to be zeros up and down from it as well. Okay, so we're going to try to get as many pivots as we can, starting in each column. So in the first column, we see if we can arrive at a pivot. And then we go to the second and the third and so forth. So let's start doing some row operations. First, I'm going to get a 1 up here in this corner to try to get a pivot there like I need for Smith normal form. Maybe I'll multiply this bottom row by a -1. And then I'll swap these guys. So I end up getting 1, -1, -4, 7. Swapping, I have 4, -4, -15, 26. Then the middle stays the same. -4, 4, 14, -24. Now I can do some airdrops. So this 1 going to the 4. So multiplication by 4 right there. Let's do that airdrop. 1, -1, -4, 7, and I have a 0. 4 times -4 plus 4 would be a 0. 4 times -4 is -16, plus 14 would be a -2, and 4 times 7 is 28, minus 24 is 4. Okay, then I do an airdrop from this row to the bottom with a -4. If I do that, I have a 0, and -4 times -1 is +4, plus -4 is a 0. -4, so it's positive 16 plus -15, which would be 1. And then I get -28 and 26, which would be a -2. Okay, now you notice that these two rows are multiples of each other, so a simple airdropping would get rid of one of these, and then what you could do is you could swap these and you get a 1 right here as we move to Smith normal form. Notice that we got a pivot here in this column. In this column, there's no pivot. We can't get a pivot at all if we leave this pivot alone. Namely, if we keep this column just looking like this, there's no way of getting a 0 here, in a 1 here by doing just row operations. So really, the pivot has to happen in this column. And as we swap those, let's see, we're going to get a 1, -2. And then over here, we'll have zeros. So we have a pivot here and here. And actually, well, almost. We can airdrop going up this way to finish it off. So let's do that. Multiply by 4 and an airdrop and make that guy a 0 right there. And -8 and 7 would give you a -1. Okay, so we end up getting this reduced row echelon form. Now, reduced row echelon form is the setting we want to be in to find just a simple, quick solution. So we were looking for scalars. X times that, Y times that, Z times that, so that we end up getting a -1 and -2. So notice that if we let X be 0, for instance, and Y be 1, and Z be -2, it works. You can try it out. Just kind of looking at it. It's nice to just make one thing 0 and then look at the other parts right here. So I'm noticing when Y is 1, say -1, and Z is -2, that'll work perfectly. So we have one solution so far. This is the first part. 0, 1, -2 is one solution to this system. Now, we're going to try to find all solutions, and we'll go to the next video to finish this off. Thanks for watching.